Okay, thank you very much. You pronounce my name better than my husband does, so I'm impressed. Okay, so today we're gonna, so in this talk, we heard a lot of talks about, or several talks about interactive coding where two parties try to talk and we want to correct for errors. In this talk, I'm going to continue this line of work, but I'm going to consider the case when there's many parties, okay, not just one. So we're many parties, we want to talk, and we still want to correct errors. Okay, and this is joint work with Abhishek Jain and Alison Leuko. Okay, so, you know, sorry, I can't, we're in Paris. I have to start again with my love story. And we started, you know, there's, you know, this love story. Bob sends Alice a love letter, and we want to make sure that she decodes it correctly, she reads correctly what he sent to her. So that's what, you know, error correcting codes are good for. To correct errors from these love letters. And as we said, the kind of gold standard for error correcting codes is what's called in the literature good error correcting codes, which such codes should be resilient to constant fraction of errors. And now, as opposed to Noga's talk, throughout this talk, I'm mainly going to focus on adversarial errors. So I don't want to make any assumptions about where the errors are. I just want to assume, the only thing I'm willing to assume is that there are not too many errors. Of course, if everything is errored, there's nothing I can do. So I'm just going to assume some bound constant fraction of the bits are errored, but I don't want to make any assumption about where these errors are. So good codes are ones that are resilient to constant fraction of error. The blow-up in communication is only constant, and the encoding and decoding should be efficient. That's kind of the gold standard of standard error correcting codes. And as we talked yesterday, you know, hopefully this love story continues, and we want to get resilient in the interactive setting. And here we defined good error correcting codes just analogously. So a good error correcting code in the adversarial error is exactly the same. We still want to be resilient to constant fraction of adversarial error anyway, anywhere throughout the protocol, and we want only constant blow-up in communication, and we want it, the encoding and decoding to be efficient, computationally efficient, so polynomial time. Okay, so, and we showed how to do this 2 days ago, but, you know, I don't know, for probably you all here are theorists, or many of you, and, you know, we're always told that our theoretical work should be motivated by you know, real-world applications. So this is my work here motivated by real-world applications. And as we know in the real world, things are not always, you know, romance in Paris. Things can get a little more complicated. And often it's not just two parties, it can be many parties involved. So this is the focus of this talk, okay? So in this talk, we're going to consider the multi-party setting. So we have a bunch of players, n players, and we're going to think of n as the number of players. And they all talk to each other in some way, and I want to make sure that even if error occurs on this multi-party network, still we can correct them, okay? So we want kind of a good multi-party interactive coding scheme. And the question is, what is good in this setting? So we said that in the two-party setting, we defined good exactly as in the non-interactive setting. But what should be the gold standard in the multi-party setting? Okay, so first, let's have the same gold standard. Why reduce our standards? I want resilient to constant fraction of adversarial error, constant blow-up in communication, and efficiency preserving. So computation it takes to encode and decode should be polynomial. Why not? So this is what we want, but if you look at it, stare at it for a few minutes, you'll see that this is clearly not possible. Why? So I want to claim there's no way you can get resilient to constant fraction of adversarial error if you think of the number of parties as non-constant. Why? Because if there's n parties, the adversary can just silence a party. He can just take one party that he decides he does not want this person to voice his opinion and just corrupt him all along. And that will be a 1 over n fraction of errors, which is okay, it's less than a constant. And so there's nothing we can do if an adversary can completely silence a party, there's nothing you can do to correct for that. So in this adversarial setting, when we don't want to assume anything about where the error is made, the only way that this kind of example shows that the best you can do is be resilient to 1 over n, or constant over n fraction of errors. Okay, just constant, think of it a little smaller than 1. just to make sure that the adversary cannot silence a party.
And N now is the number
N now, yes, N now is the number of parties.
And the communication model is full connectivity?
I'm going to get to the community. Okay, good. So there's a very good question here that was asked. What is the model here? Because in the multi-party setting, there's a lot of models. I'm going to get to the models in a minute. Okay. Okay. So that's what we do. We show that in the multi-party setting, we construct a interactive coding scheme that is resilient to constant over n. N is the number of parties, fraction of adversarial error. The error can be anywhere. There's only constant number, constant blow up in communication, and it is the computation is efficient. It's efficient preserving, so polynomial time overhead. But there are some assumptions, and before I get to the assumptions and the network, but before I get to my assumptions and the network, let me first explain the model. Okay, so how are we communicating? We're n parties. How are we communicating? So here's the model, okay? So first, okay, we're n parties. The first thing I'm assuming, and this is kind of a standard, it's often assumed, if you don't assume it, things become very complex. Also in distributed computing, this is often the assumption, not always, but often, is synchronous. But what is the synchronous assumption? You just assume the only thing, when I say synchronous, what I mean is that there's clocks and kind of rounds, that the protocol proceeds in rounds. And in each round, some parties send messages to some parties. Okay, so it's kind of point to point, and maybe in round 1 I send Boaz a message, maybe in round 2 he replies, maybe not, maybe, you know, I sent to some parties that I'm connected to. I don't have to be connected to all. It's not clear that I can send messages. I only can send actually messages maybe to my friends, and I don't have to send messages to all my friends at any point of time. So it's some protocol where I send messages to the people I'm connected to whenever I want to, and everybody else does the same. Okay? And I call this the synchronous model, even though in a slide or two I'll show you this is not in coding theory. A synchronous model often refers to something else. So there's two communities. There's the coding theory community or the information theory community, and then there's the distributed community, distributed computation community. And I think they use synchronous in different meanings. So this is how the people in distributed computing think of synchronous. Okay? It's a bunch of players. They send to each other messages whenever they want. There's no obligation to send or not to send, but the protocol proceeds in rounds. Okay, that's the model I'm referring to.
Can silence be used to communicate with somebody was saying yesterday? Assuming silence can be used to communicate? Or?
Okay, no, I do not want to assume silence can. That's a very, very good question. I'm actually going to get to this point at the end of the talk. The question was, can silence be used to communicate? And no, the silence cannot be used to communicate, and it should be, I'm going to get to this point at the end of my talk, but no, silence cannot be used to communicate. Yes?
Also, like the fact that we can only tolerate constant over n number of actual bit is perhaps because you haven't parameterized the number of parties involved. Like the number of parties, it's happened here because the extremal examples are when each party communicates a constant number of bits, and that's when things go wrong, right? Whereas often if the length of the transcript is much longer than the number of parties involved, then
no, but still, suppose the length of the length of the transcript is t much bigger than n, and everybody sends many, many symbols. Still, by corrupting t over n, you can corrupt one party. Now you can ask, you know, what if the distribution of corrupting is different? And I'm going to get to that point too. Actually, thank you very, very much for the questions. So actually, yesterday I had a discussion with one of my colleagues, and he told me, you know, when do you know that you're giving a good talk is when people predict your next slides. So thank you. Okay, yeah, so this is our model. So, you know, at each round, some players send messages to some parties. And here's our assumptions on our theorem. So we said we construct a multi-party interactive coding scheme with kind of a good, for us, what's the gold standard in the case of adversarial error. So 1 over n. N is the number of parties. Just note, by the way, that this extends the result for 2 parties. Okay, so for 2 party, n is 2, so this is constant. Okay, so for constant number of parties, it clearly extends the result for 2 party, and for n parties, that's kind of the best you can hope for in the setting of adversarial noise. Okay, but we have 2 assumptions that we make. And again, these assumptions extend the two-party case. So the first assumption goes to Buz's question. We assume that there's one, in the network, there is one party that's connected to all. And this is very crucial for our technique. Okay? We assume that there's one party, we call him P star. He knows everybody. So in some sense, to get a result, or the way we get a result, we take one party and he's our coordinator. He's going to help us correct errors. Okay? So we have this coordinator, P star, and we assume that he's connected to everybody. So in a network where we don't have such a coordinator, our result does not hold. Okay? So that's the first assumption. And the second assumption is that we have this. The second assumption is actually an assumption on our original protocol, and our assumption is that the protocol is semi-adaptive. And what do I mean? So it's not fully adaptive. And what do I mean by it's not fully adaptive is I assume that whoever speaks at any point to the people I send my message to does not depend on the content of the messages I received. So what I send, so when I send a message to Noga, what I sent her may depend on what she sent to me. But whether I send her a message or not does not depend. So I'm going to send her the message no matter what she told me. The content may depend. Okay, so we call that semi-adaptivity. So in other words, we know ahead of time who's going to send who messages. And that's very important for us, that P star knows who you're going to send messages to, otherwise he won't be able to orchestrate his kind of the show. Yes?
Some of the previous messages have been corrupted?
Yes, it's okay that the content are corrupted, okay? But I need to know who you plan to send the message to. Huh? The traffic pattern is non-adaptive, exactly. The traffic pattern. What? Okay, so we assume it because we need it, and now you can ask, why do we have such a star network? So look, if you don't, you can't do it. It's the result says if you have a party that's connected to all. So another way, we're saying we're a bunch of players. If you want to, we propose a way to correct errors. If you want to run, if we people are afraid of errors, I propose Noga, send everything through Noga, and she'll help us correct the errors. That's kind of the proposal. No, actually, I'll show negative results showing that in some cases this is impossible. So in some, yeah.
But it doesn't extend to the fully connected graph with leader election.
A fully connected graph in particular has a graph star. I assume that there's a subnetwork that has a star. So I take any protocol.
And
you
the
can.
negative P star is fixed and known ahead of time?
Yeah, so we elect a leader in some sense. So we say Boz is our leader. Now we're going to send everything through Boz. But my assumption on my original protocol is not a star. So in the original protocol, we just talk to wherever. I just want to make sure, to make it error resilient, I want to make sure that there's one party that's connected to all, and I'm going to use him in the error resilient protocol. So in particular, if you have a full graph, in particular, it has a star subgraph. So our result holds for the full graph, of course.
That's interesting. Yesterday, Klim's talk showed about, talked about how the star network is actually the worst integration, right? It seems like.
Yeah, exactly. I'm gonna mention Klim's and a friend's result in a minute. Yeah, but Klim shows a negative result on this star network, which I'm gonna mention in a minute. Okay, so this is our result. Any more question about this result before we move on? Okay. Good. So previous and follow-up work to ours, and I'll put this in context, and with Klim's result and with other, there's been a lot of result on this. So first thing I want to mention, there's been a few other papers on this topic of multi-party interactive coding, and all the other papers also consider synchronous model, but different than ours. Okay, so the synchronous model that they consider is the one that's more aligned with information kind of theory, a line of thought or community. And there they also assume that the protocol proceeds in rounds. That's the case for any synchronous protocol. Protocol proceeds in rounds. But in there they assume that actually in each round, all parties send messages to all other parties. The point is, what they count is the number of rounds in the protocol. They don't count the communication. So when they propose convert a protocol into an error-resilient one, they want to know what their blow-up, how much they pay. They only count the number of rounds of where the protocol of increase. Okay? They don't count the communication. So if they started with a protocol where very few people send messages, and they ended with a protocol with more or less the same number of rounds, where everybody sends messages to everybody, in this model, it's not a blow-up. Okay, so if in each round now you send a lot of messages, they don't care. They don't care about communication. They only care about rounds, and they only measure rounds. Okay, so our work is different in that way. I think our work is more motivated by distributed, or I'm a cryptographer, and that's in cryptography we really care about also communication complexity and rounds, the communication. So I'm motivated more from the crypto side or the distributed computing side of things. So that's what we measure. We care about communication as well, whereas other works only cared about rounds. Okay, so now let me tell you what was known. So the first work on this topic was, of course, Schulman, because he has always the first work. So it's Rajgopalan and Schulman. And what they did, they constructed a multi-party interactive coding scheme for arbitrary topology. So they didn't need to assume any star, not star, nothing, any topology you want. It was for stochastic error, so random error. Okay, each bit is flipped with some epsilon probability, so no adversary. And the rate was order 1. Okay, so they got the number of rounds, the increase in communication, the error rate, so they could, the epsilon, the error rate is constant. Okay, so we get 1 over n, or constant over n, they get constant. But there was a blow up in the number of rounds, which is log the degree, the maximum degree of the graph. Okay, so in particular, if you think of full graph, the blow up in rounds is log n, but now everybody sends everybody a message. So the blow up in communication can be as big as n squared log n. Okay, if you count communication. Okay, so it can be quite a large blow up. And their protocol was inefficient, but later using potent tree codes, which Angelis talked about, so using the work that did potent tree code, they can make it also computationally efficient. Okay, so this was the prior work to ours and what inspired us. But then after our works, there have been a bunch of follow-up works. So the first one is a paper by Hoza and Schulman, where they also did adversarial noise, like we do, but they considered, again, arbitrary topology. Okay, so they did not want to make any restriction on the topology. They considered arbitrary topology, but again, there was a blow-up in the rounds, and the blow-up in the rounds was the number of edges in the graph times log n over n. N is the number of nodes in the graph, the number of players. M is the number of edges. And again, this is round blow up. So if you think of communication, this can blow up much more. Okay, it can blow up by m. So m squared log n over n. And their error rate was the same as ours, and the result was not efficient. So they used tree codes, which makes you not efficient. Let me actually say one thing. Our result that I'm talking about in our paper that we have, it's not efficient. And the reason it's not efficient, we also use tree codes. However, a few months after our results was posted, Hopler posted his result. And then we could have, now we know how to use, with Hopler's results, we can make it efficient. And I'm going to present the Hopler kind of the efficient version of it. Okay. And then very recently, there's a new work, very nice work by Alon et al. And they assume a complete graph. Okay, so in particular, you can think of a star, but it's more general than a complete. They have a kind of a friends of complete, so close to complete. It's a little more general than the complete graph. It's again for stochastic error. And they get constant blow up and round and constant error rate. And it's efficient. But again, the communication blow up is going to be like n squared. So their idea is, even if you were sparse, now send to everybody and hope that kind of, if I want to send a message to Boaz, the idea I'm going to send to everybody, everybody's going to send to Boaz, and it's going to arrive in so many ways that Boaz will be able to kind of error correct it. That's kind of the idea. So in every round, there's kind of everybody sending, everybody messages. That's the idea. So again, blow up in communication. Okay, so this is the works on the positive result that we have in the multi-party setting. now back to your question about Klim's results. So Klim showed yesterday, he presented a very nice work that he has with Breverman et al., where they showed a negative result. They showed that if you don't, there exists network, and actually for his, it's the star network, that in the star network, if you have a star network, just a star, okay, so one party connected to everybody else and that's all, there's no hope to get constant error rate with constant blow-up in communication, okay? There's just no hope to get it. And it's somehow kind of shows that the 1 over n, even for random error, it's not 1 over n, but it's, for them it's 1 over log n for random error. But in the star, you can't get constant error even for random error, okay? So, but recall, we don't get constant, we get 1 over n. That's how we get, that's how our result fits in with their result. Constant error, it's impossible, we get 1 over n error, okay? Let me also mention, actually, in this work together with Jane and Leuko, we also show a negative result. But our negative result is not really a negative result. It's a fake one. So it's a black box negative result. It just shows, what we show is it would be hard. I don't want to really go into what black box reductions mean and so on. But essentially, I think I'll leave you with this message. So we showed, okay, you can silence a party in different adversarial errors. There's no hope. You have to pay the 1 over n. But then we asked ourselves, okay, why not just assume that adversarial error, but let's assume the adversary cannot silence a party. So every party adversarially error, but you can only corrupt the epsilon fraction of each party's communication. That's reasonable. You know, it's not too restrictive, and that's the best you can hope for. So why not this model? That seems like the best model. And we show very serious caveat that would be hard to construct. So we don't have a full-fledged negative result, but we kind of give an intuition that, you know, using known proof techniques that we have, which are always kind of black box proof techniques. So using proof techniques, known proof techniques, you won't be able to show such a result. So, okay, so we're gonna stick with ours, okay? So again, you know, we assume that there's a star subnetwork, so there's one party that's connected to all. He's going to help us execute our protocol, and we're going to construct a protocol that's resilient to constant over n and the number of players, adversarial error, constant blow-up in communication, not only rounds, also in communication, and it's going to be efficient. Okay, questions before we start? Okay, so, you know, I don't know, for those who were in my talk 2 days ago when I talked about doing efficient two-party interactive coding, we don't really know, so, you know, as I said, I'm a cryptographer. In cryptography, we never actually prove anything. The only thing we know how to do is reductions. Well, we can do this if we could do this. We can do this if this is true. So in that spirit, I always make I do reductions, you know, so on Wednesday I showed if you have a exponential time coding scheme, I'll use that to make it polynomial. In this talk, I'm going to reduce it to the two-party setting. So I'm going to say, well, if you have a two-party interactive coding scheme, I'll use that to make a multi-party coding scheme. Okay, so how do we reduce it to the two-party setting? Okay, so I'm going to use the two-party one. How? First idea that comes to mind, well, any two parties that are connected don't just talk freely because, you know, you may be corrupt. I mean, bits may be corrupted. Use Schulman or any interactive coding scheme you want and talk this way. And that's kind of the basic idea. However, this does not work for two reasons. So the first reason is that now the number of communication links between us may be very, very large. So in a full graph, it'll be n squared. Okay, so n squared communication links. And that, as we'll see in a minute, that's way too much. There's no way we can be resilient to 1 over n fraction of error, or epsilon over n fraction of error, with so much communication links. Because there may be error in this communication link, and we won't know that until n squared, you know, error will happen somewhere else in the network. And then we'll need to correct that, so we'll need to pay n squared. So again, the thing that's important, let me actually, before I start, the intuition, the thing that's very hard in the multi-party setting is that an error can happen in the West This will affect what happens in the East. But you won't, so Boaz may inject an error, was corrupted and an error happens. Now everything we talk, we listen to Boaz. Whatever he said, we continue with that. Now we talk, everything is meaningless because that's not what he intended to tell us. Okay, so he tells us, talk about literature. Now this entire concept about literature. But that was corrupted, he actually wanted to talk about interactive coding. So all this is garbage, we need to go back. So whatever one person says may affect the entire network. And so if there's n squared links, and order n squared links does not include the corrupted party, then n squared communication goes on before we even notice that there was a problem. And so we pay for that. So that's too much. We can't afford more than order n. And the reason we can afford order n links is because we only assume 1 epsilon over n fraction of errors. So that's too much. And another problem that we'll deal with, and you'll see how we deal with it, is that we need to synchronize. It's not enough that me and Maya talk between ourselves and do an interactive coding, because we need to somehow simulate ourselves with the rest of the world. So if I talked with Maya, but then I noticed, oh my God, there was a mistake. I need to tell Maya everything we talked about was irrelevant. Go back. Okay, so we need to somehow synchronize ourselves with the rest of what the other people are saying. So these are the issues we're going to deal with. Okay, so how are we going to deal with this? So the first idea, that's where the star comes in. We're going to have a coordination-based approach. So we're going to assume that there's one party, we'll call him P star, assume everybody knows who it is. It's the party whose, his name comes first in the alphabetical order. If everybody's connected to everybody, then just choose some arbitrarily. And now the first thing, I'm going to assume that all the traffic goes through P star. Okay, so in other words, if you started with a protocol, let's say that P1 sends a message to P3, and now I'm going to tell them first thing, before you make it error resilient, don't send anything directly to P3. If you want to send a message to P3, send it through P star. P star will deliver to P3. Okay? And I'm going to assume that P star knows who to deliver to because the traffic is determined ahead of time. If it wasn't determined, then there'll be another log n blow up in communication because P1 will need to tell P star who to send the message to. So that's why I'm assuming traffic is determined ahead of time.
And if messages are large enough, say each message is at least log n bits?
If messages are long enough, I think we don't need the assumption that, yeah. In other words, if you're willing to have log n blow up in communication,
Messages are large enough and the log n is additive.
Yeah, so right, exactly, yeah. Yeah, you can do the same where just append to each message the person, and that will work. Yes, you're right, exactly. Okay, so this is first thing. Okay, so I'm going to tell you how to make your protocols error resilient. First thing, send all the messages through me. I know you all, I'm going to deliver your messages for you. Okay, don't send it directly to each other. Because if you send it directly, you won't know that there was an error. I'll correct the error, I'll help you, I'll tell you if there was an error. If there was some error in the protocol, I'll let you know and tell you to go back, and I'm going to do all the synchronization for you. Okay, so that's the first step. Okay, so now everybody only send your message to me, I'm P star. Okay. Now when you talk to me, don't just talk to me regularly, because our channel may be corrupted. Use some interactive coding scheme. Okay, so we're going to use a two-party, just between you and me, coding scheme. And for you guys, you just use the coding scheme as is, the one that Hopleo. That's it. I will need to work a little harder than you guys because I'll need to kind of coordinate everything. But for you, from your perspective, you just use Hopleo's interactive coding scheme. Okay. So that's the idea. But there's two small problems. One problem, which I said, is I need to somehow synchronize all this, and I need to explain how to do that. Okay, so that's what we're going to do next, explain how to do that. And then there's another problem. This is a small problem because it's very easy to correct, and we'll correct it right away, is that what if one party speaks, he's corrupted, and then he doesn't speak again for a long, long, long time. So in other words, I'll go back to the example. Suppose Boaz says, this conference is about literature, and leaves, doesn't talk anymore. And now we go on talking n third times or whatever about literature. But Boaz doesn't even have a chance to say this was an error. That's not what I meant to say. So we need to give every player in the room the ability to shout, you know, something went wrong. Okay? So we'll do that. So we want to make sure that errors are detected fast. After at most, order n bits are transmitted in our network. Okay? So because errors can happen, again, every epsilon over n bits an error can happen, I mean, on average. So we want to make sure that every order n bits, each party gets a chance to yell that there was a mistake and things are not going well, to tell P star, to tell the coordinator, things haven't gone well. Okay, so that's what we'll do, and this is a very easy problem to correct. The way we're going to correct it is in the original protocol. We're going to just assume after every n bits are sent, or order n bits are sent, just each person send a 0, or a constant number of bits, just a bunch of zeros. In the original protocol, there's no point to these zeros. But in the error-resilient protocols, they're going to use these zeros to actually say, problem. Okay, that's kind of where this just gives the ability of each player every n bits to yell that something went wrong. Okay. So so first thing we do, we're going to change the protocol so that every order n bits, each player sends order 1 bits. First thing, just a bunch of zeros. And then now the communication goes through me, through P star. Okay, good. Now, so that's our protocol, and I'm going to make this one error resilient, right? By using two-party communication. So now everything is through me, and I'm going to talk with each one of you via a two-party interactive coding scheme. The question is, which one do I use? Okay, we have several. And it turns out I can't just use I can't use a two-party, unfortunately, I cannot use a two-party interactive coding scheme as a black box. Why? Because there's this P star who needs to somehow synchronize with all of this. So I can't just use, I need to kind of change it a little bit, that P star will be able to kind of synchronize between all these two-party interactive protocols. So let's see which one to use. So in our paper that we published, we used Schulman, and it was inefficient. That was the drawback of using Schulman. Schulman is, there's an exponential computation time overhead for using his protocol. Okay, what we really wanted to use is the work with Poincaré because that was efficient. But it turned out we could not use that. When we tried, we got a log n overhead in the communication. It blew up the communication by log n. And I'll tell you intuitively why that's the case in a second. But it turns out that with Hoppler, which is efficient, we can do it. Okay, and today I'm going to present you the one with Hoppler, okay, not the one that's in the paper, because that's efficient, it's better. And we didn't use Hoppler because he came a little after us. He published his result a little after we posted ours. But let me tell you why, for example, the work with Poincaré, we couldn't use it, we didn't succeed. And the reason is, for those who remember a little bit, you know what, let me first recall, we're going to use Hoppler. Let me first recall the Hoppler construction, because we'll need it. And as I recall the Hoppler construction, maybe I'll say a word about why the work with Poincaré could not be used. Okay, so what we do, so just a recall, so the first step we do to get an error resilient, we first convert the protocol so that every n steps, each player gets an opportunity to send constant number of bits. All the communication is through P star. And now, so now suppose P1 wants to send P3 a 0, it sends to P star. P3 wants to send P6 a 1, it sends through P star. Wait, hold on, sorry. Yeah, okay. Okay. And now the second thing we use Hoppler to do a two-party interactive protocol. So how does Hoppler work? We need to recall how Hoppler works to do this. So recall the way Hoppler works. I mean, I didn't say much about it, but it's very similar to the construction with Zwicker. We do a small chunk In the work with Zvika, we did it using a tree code, this chunk. But in Hopler, it's only constant number of bits. You can just do it in the clear. Don't encode anything. Just send constant number of bits in the clear as is, and then check that you're consistent. Check. So you record these bits, you send a kind of a small hash, you make sure you're on the same page. If so, you continue, you send a few bits. And then you check that you're on the same page. If so, you continue, and so on. If there's a problem, you go back. And how exactly you go back, how this consistency check works, actually it's very complex in Hopler's protocol. I don't want to get into it, okay? But that's kind of the idea, okay? In the work with Zvika, these were not in the clear, these were encoded. This was a chunk of size log n. The consistency check was very simple compared to Hopler, much simpler, because we could have consistency check of size log n. It simplifies our life by a lot, okay? But this is encoded. And the problem in the multi-party setting, if each chunk is encoded, then now suppose we're n parties, okay, and I send them, it kind of goes in circle or something like that. I send a message and then you send a message and so on. Now, even if my first message, only one message was corrupted, I don't have log n to correct it. So we use a tree code and the first message may be corrupted. Now, what do you guys do? And if with one corruption, the adversary, with an error correcting code of size log n, one corruption should be detected and corrected. It shouldn't make us go back. Only log n corruptions are allowed to let us go back, or order log n corruption, not just one in a chunk. But when we plan the attractive setting, even one, I don't know how to continue. It makes things just not work.
So what's the difference between order while order of?
Because in order 1, if there's n parties, we can assume that in most of the chunks, let's say we go in a circle, we can assume no error happened. In many of the circles, no error happened because only order n bits were transmitted. And the error rate is only epsilon over n. So for most of the rounds, we can assume that no error happened.
Wait, but you had the same problem in your paper. What's it?
Because with the paper with Zvika, our chunks are of size log n. And we assume that only constant log n bits of error happen. Now, because of the encoding. But suppose I send only my first message, I don't send all my log n messages. I send only one, and it goes around for n people. And then around for n people. So I start my encoding, my tree encoding, but there may be one error, even one error. My first message was an error. So now it's delivered in an error. But in the work with Zvika, we're correcting it.
But if you add some exponential mechanism to encode everything, all the log n.
Then we log n blow up in communication, which is, we could do the work with Poincaré with log n overhead in communication, but this is exactly what we're trying to avoid. So the fundamental difference between 2 parties and n parties is that in n parties, I can assume that from the time, when I send a message, and even one message, n messages are going to be sent after me. I can't assume I can correct it before it goes out to the world, because it's just one message. It can be corrupted. And if it's corrupted, I'm gonna spend n messages are gonna be wasted. But in Zvika, the work with Zvika, every chunk there's one corruption, of course. So now everything is corrupted. Because we assume at most log n, epsilon log n, but not, the chunks are big enough that every chunk will be corrupted. That's kind of the issue. Okay, but for those who that doesn't matter, we use Hopler. And I'll explain to you why Hopler works. You don't need to understand why the other doesn't work. I'll explain why this does work. Okay, so this is the basic idea behind Hopler's scheme. And now I'm going to explain how to use this in the multi-party setting. So here's how it goes. We have many parties, okay? As I said, everything is going to be through P star. And here's how we do it. So here's the implementation of Hopler. Send messages in the clear. Order 1 messages. The first 10 messages are in the clear. So when P1 wants to talk to P3, he sends 0, I send to P3. You know, he sends me 1 in the clear, 1, blah, blah, blah. Now we did our 10 messages. Now time for consistency check. So now P1, let's say, does a consistency check with P star. He tells him, you know, all his information to make sure they're consistent. P star tells him also the consistency information. If they agree, they continue. If they don't agree, then now they go back. Okay? That's just the idea. And now the important thing here, each PI just behaves as in the protocol of Hopler. He doesn't even know. He doesn't, from his point of view, he's interacting with P star. The fact that P star is interacting with the entire other world, he thinks of P star and everybody else as one party. So he really, the only thing he needs to know is Hopler's protocol. P star, on the other hand, needs to be a little smarter than that. And he needs to kind of orchestrate everything. So P star, each PI, he always, that's how it is in Hopler. This is an oversimplification, okay? There's a lot of more things going on in Hopler, but I'm kind of giving you a baby version of it. Each party, he always keeps in mind, so we're trying to run the original protocol. He always keeps in mind kind of a partial transcript of the original protocol, where in the original protocol he believes they're in. Okay, so originally the TI of PI is empty. We didn't start. The TI is the transcript. So far we didn't do anything. Now I send a message 0, I believe the transcript, I append 0 to the transcript and so on and so forth. And then when the consistency check fails, I'm going to go back, I'm going to erase some of the transcript because I know it was malicious, there was error there, so I'll go back. And there's this game, that's how Hopler works. Okay? P star, that's kind of the difference. That's what P stars work. P star is going to keep a partial transcript with all of the parties. So he's going to have T1 star, T2 star. He's going to kind of, he talks with everybody. And now, when he goes back, when he finds, oh, there was a problem with P1, and I need to go back, he knows that he may also need to erase part of the other transcripts as well. So he goes kind of to the, he erases the, even when he only talks to P1, he may update all of the transcript, T1 star up to Tn star. Okay, because if he saw there was a problem and he goes back, that corresponds to kind of reverting the protocol with the other players as well. Okay, so that's how he kind of orchestrates this entire protocol. So again, when the consistency check fails, P star adjusts all the other transcripts. That's the idea. That's the basic idea. Okay? And now the reason this works, the intuition, and that's where the Brakersky one won't work. So here's the idea with analysis, just one slide. I'm not going to go into it because actually it's quite simple. The high level idea is simple.
What's adjust? Rolls back all
Rolls back.
messages?
Exactly. So if we talked and I realized there was a problem and your message influenced after that what, you know, a bunch of the other things happened, all these things that happened after that that were influenced by your bad messages, I'm going to roll back. I'm going to erase from the other people's protocol, from the PJ stars of other.
Or because of independence?
Because of the dependence, exactly. Exactly. Okay, so like for example, let's go back to our example where Boss had this conference about literature, and then everybody sent me a message about, you know, Hemingway. Then, you know, after he talks again, says, no, this is interactive coding, I'm going to tell everybody, I'm going to revert back to the initial and tell whatever, everything was wrong, and you'll need to go back, and then everybody's going to talk about interactive coding. Okay. So, and in the analysis, the way the analysis goes, it's this potential function analysis. It's a simple technique that I'm, you know, used all over the place. And the idea is the following. I'm going to partition all the transcript, this entire multi-part interactive protocols, into chunks. Of each chunk is going to be of length order n bits. So I'm going to look at the first order n bits that were passed overall in the protocol, and then the other order n bits, and the other order n, and so on and so forth. And I'm going to show that every order n bits that passed, progress was made. Okay, and I'm going to show that enough progress was made that after the desired time, we're done. Okay? And what do I mean by progress was made? I'm going to show either in this order n bits, no error happened, okay? In which case, we made progress because there was no error in every order n bits, progress was made if there was no error. And if error did happen during this order n bits, then now the adversary has a smaller, error budget. Okay, so we made progress. Now we're dealing with adversary with smaller error budget. I just want to point out for Noga, this is a personal, because in the Tzvika case, the case 2 does not hold. Because if one error does not make him smaller budget, that's the, okay, but that was a side. Okay, so that's what the analysis is simple. So, okay, so I don't want to go into it too much. I just want to summarize and say that what we do is we construct an interactive coding scheme in the multi-party setting. We get resilience to constant over n. N is the number of parties, fraction of adversarial error. For the general adversarial error, it's optimal. It seems like to get over this barrier for per party seems kind of hard. We get constant blow up in communication, and its efficiency, this efficiency preserving is, you know, not in the paper, but it's going to be. And we have two assumptions. One is that there's one party that's connected to all, and the second that we know the traffic pattern is known. And now, before I end, I want to go back to your question. And this is an important one, which is now that people can talk, one can say maybe silence is information, and now the adversary can't corrupt silence, so that's a bit of a problem. And actually, in our review, we got a very interesting comment. It was by Hoza-Schulman, and they phrased essentially this concern, but in maybe a little more. A different way, and they said the following: well, you have so many links between you guys, your n parties, many links. Why don't you use links to communicate securely? So for example, and they say if you can do that, you trivialize the problem. So for example, suppose I had 2 links connected to each one of you. Suppose we had 2 links. Why? Let's just talk with 2 links. Why just 1 link? Let's use 2 links to communicate. And now I'm going to tell you, when I want to send a 0, I'm going to communicate it through the left. And I don't care what I send there. If you hear something from the left, no, it's 0. The adversary can corrupt it, for all I know. But if it comes from the left, it's 0. And if it comes from the right, it's 1. So if you add links, and this is, by the way, also true in the 2-party setting. Okay, let me tell you how to do secure communication in 2-party setting. Don't even worry. Just add the link. Now when I talk to you from the left, it's a 0, and talk from the right, it's a 1. The adversary, don't even listen to what I say. Just kind of try to see from which ear you hear it. And now you're done. So what this point says is that, so you can add a link, and you know, this is going to be for one message, is going to be 0, and then the adversary, because the adversary model that we consider is just the adversary can flip. Either it's random or adversarial, but flip. So it's a problem. So what it says is what you really want is to be resilient to insertions and deletions. And we get resilience to insertions and deletions. And it's going to be written soon, but it's on its way. And yeah, so that's important. And by the way, before I end, if anyone knows what is the best error rate you can get for just one-way communication with insertions and deletions, please let me know, because it seemed like Goswami is the best? Okay. Okay. Thank you very much. Oh, and her too. Thank you.